Hello, welcome to my videos about the DICE climate model. What I'm going to be doing for the next 3 videos is walking you through how to build a climate model in Excel based on Bill Nordhaus's DICE model, the climate module within Bill Nordhaus's DICE model. This is going to be how you're going to simulate the effect of an extra ton, or really a whole bunch of tons in, say, 2020 or 2025, and figure out what the social cost of carbon is associated with those tons that are emitted. So we're going to be going back and forth between some slides that kind of talk about things and help me make my point, and this spreadsheet here, which you could have downloaded from Sakai. Let me start by noting that in the spreadsheet, these are all the kind of starting values that you need to do a simulation. And the yellow is just highlighting all the stuff that you're starting with that we're not going to calculate in these videos. But I should highlight that the thing that you've been working on in your group has been to forecast the CO2 emissions. It's the very first column here. And I'm starting with some values here that we can use, but we're going to see these are this is a very bad scenario. I don't think the emissions are actually going to be this high, but we'll play with this and see what happens. A second thing I should just start by noting is that the emissions in this spreadsheet need to be in gigatons of carbon, not carbon dioxide. To convert your projections of carbon dioxide into carbon, you need to divide by 44, the molecular weight of carbon dioxide, and multiply by 12, the molecular weight of carbon. You don't have to understand the chemistry, just make sure that you're projecting gigatons of carbon when you paste your data into column B on this spreadsheet, which is the first thing you should really do to get started. And you should just double check that the starting values in 2005 and 2015 and 2025, that these numbers are around 10 gigatons and not around 30. If they're around 30, you've still got carbon dioxide, and the model is not the coefficients don't work for carbon dioxide. Okay, so let's go back to the story. So the first thing you're going to do is take the fossil-based emissions that you've calculated, what's called industrial emissions here, and add them to land use emissions. We're not going to build a model. We're not trying to build a model of land use emissions. That's from deforestation and reforestation and things like that. But we're just going to take a set of emissions that are out there and add them to the industrial emissions that you've projected. So the very first thing we're going to do is just add industrial emissions and land use emissions, and then copy that cell all the way down to 2035, to 2305. Okay, so that's our emissions. The next part of the DICE model is the atmosphere and the oceans, these reservoirs of carbon dioxide. And the idea is that in the DICE model is that there are 3 reservoirs. There's the atmosphere, which is the layer that we're emitting the carbon dioxide into. Below that, there's the biosphere and the upper oceans. And then at the very bottom, there's the deep oceans. And the idea is that CO2 each period mixes between these 3 layers based on different coefficients. So all the CO2 in one layer has to end up somewhere. It either stays in the layer it started in, or it moves to the one either above or below it. Okay, and so you can kind of see from this formula that the model says that the atmospheric amount of carbon in a given period is equal to the emissions in that period plus the amount in the atmosphere and the upper oceans in previous periods times these mixing coefficients. So the way we're going to write that here is that the atmospheric concentrations are equal to the amount in the previous period times this coefficient over here, which is the mixing coefficient, how much stays, and we'll give it dollar signs to keep it fixed, plus the amount from the middle layer times the amount that transfers from the middle layer to the atmosphere, again with dollar signs, plus the amount of emissions one period before times 10, because there's a 10-year time step in this model, and these are annual emissions. So we need to multiply those emissions by 10. Now, going back to this formula, just one thing I'll note here, if you were paying close attention, is in this formula, it says the concentrations in period T are equal to the emissions in period T plus the lagged or the previous period values of the amount in the different reservoirs. And when we did the formula right here, we actually used the amount of emissions from the previous period. And I just wanted to assure you that is actually not a mistake that I'm making. That was a typo in the manual that Nordhaus wrote. If you look in the appendix and you look in the code for the model, he actually does it the way I've done it in the spreadsheet. So if you, again, you look at the formulas here, it's for the middle layer, it's going to be the previous period values of each of the reservoirs times the relevant transfer mixing coefficients. So I'm just going to type here that the amount in the middle layer is going to be in 2015 is the amount in the upper atmospheric layer in 2005 times this amount that moves to the middle layer plus the amount in the middle layer in 2005 times this coefficient about how much stays plus the amount in the very deep oceans in the previous period times the amount that rises back up. And then I'm going to do the same sort of formula for the lowest layer, which is just going to be the amount in the middle times the coefficient plus the amount in the bottom times the coefficient. That is, it's going to be this amount in the previous period times the amount that gets transferred to the deep oceans plus the amount that was in the deep oceans times this very large fraction that stays. And just to point out the obvious, each of these sets of numbers has to add up to 100%. There's a conservation of CO2. I guess it could actually become some other, it could decay and become some other chemical, but that's a very trivial amount. So these are basically adding up to 100%. So once I have these three numbers, I can copy them and fill the rest of the table. The last thing I'm going to do in this video is convert from the mass of carbon in the atmosphere to a concentration. And as you can imagine, there's just a straightforward constant that converts. It's right over here. That is, every part per million is equal to 2.13 billion tons of carbon. So I simply take the amount of carbon in the atmosphere in billions of tons and divide by this number in order to get the concentrations in ppm. And that's a number that we'll need later on for a formula. So it's just kind of easier to keep in mind. And just for reference, before we started burning fossil fuels, the concentration was about 280. And when we double CO2 in the atmosphere, it'll be about 550 parts per million. And those are kind of numbers you might want to have in your head.